Thanks a lot, Michael. It's a great pleasure for me here to be here in Krakow and to be able to present some of my recent work here to you today. I've been working on visual perception for a long time now, and I've also studied eye movements for a long time. But until very recently, these two things were really running in parallel and very separately. And it was only when these two Italian postdocs came into my lab that those two lines of research converged, and I've come to the conclusion that we can really fully understand visual perception if we take the movements of the eyes into account. Now, previously I mainly studied eye movements in the context of their motor properties, or how different visual stimuli would change the motor properties of the eye movements. And for visual perception, basically the one common factor that's constant over more than 100 years of research on vision is this little fixation spot. And basically most of the method sessions always start at the beginning of the trial. A small spot was presented at the center of the screen. So basically in experiments on visual perception, what we mostly try to do is to keep the eye of the observer fixed at one location. And of course, when we look around in the real world, there's no fixation spot dangling around. So there's probably a reason why people use the fixation spot, and it's a very simple reason. The reason is that the retina is not homogeneous at all. Instead, if you look at the distribution of photoreceptors across the retina, here's the density of the cone photoreceptors is plotted on the y-axis. You see that they're very densely packed, close to 100 or 200,000 cones per square millimeter at the center of the retina in the fovea. And then as you go away from the fovea, very quickly the density declines, and here in the visual periphery there's about 2,000 cones per square millimeter of retina. And of course the cones are the receptors that underlie our daylight vision, and basically our visual acuity changes in a similar manner to the density of the cones here. So what this means is that we really only have a very small region in our visual field where we have very high acuity, where it's about the size of your thumbnail at arm's length. That's where we can read the newspaper or recognize individual faces. Now, of course, this will be very difficult for us. We only see things really well in this small spot, but there's a second design feature of our eyes that allows us to get away with this small foveal region. Namely, it's the muscles that are attached to the eyeball, and they basically allow us to place the fovea very quickly into different parts of the visual field wherever we want to pick up information. And just how badly we really need these eye movements is illustrated here in this two-dimensional representation, where the fovea is plotted here, and the region that you can see here is basically the binocular visual field. And so basically we really only can get high information from this very small region, and outside of the fovea our visual acuity and other aspects of vision are very much handicapped. And it's the movement of the eyes that allows us to reposition the fovea then quite quickly. Of course, you might say, well, if I look somewhere, I still see everything and it looks just fine. But I'd like to illustrate to you that this is really only an illusion that in the end is enabled by our eye movement. So what you see here is Gießen University, or at least it's a small part of Gießen University. It's our convention venue. And I'd like you to fixate here at the center, at this red spot here, and then just keep fixating there while I change the picture. And when you still fixate here, the second picture will look very much like nothing much has changed. But now if you move your eyes around, you can see basically that all the contours in the periphery are rather crooked and nothing is really straight anymore. So before, when you look here in the center, you have this illusion that everything is there, but even though it's not really there in the way you would have predicted. And I think what our visual perception in the periphery, where the sensory signals are relatively poor, mainly is a prediction. And I'm going to present to you in the second part of my talk the mechanism that allows us to learn this prediction. But what this should also illustrate is the need for us to move our eyes around. And the eye movements we mainly use are saccadic eye movements, which are some of the most frequent movements of our body, about three or four times per second. And they're also amongst the most precise movements of our body. And we execute those saccades, of course, to foveate objects, to bring their representation onto the fovea. And of course, the big benefit of these saccadic eye movements is immediately to improve the acuity for the foveated object. But of course, they also have some disadvantages. And one disadvantage is that the eyes move very quickly. The retinal image the image of the world moves very quickly across the retina, and basically we cannot see anything or hardly anything during the movement of the eyes. And if you add up the time we spend during the saccades, 50 milliseconds each, it's about 1/5 of the time that we're functionally blind. And the other big disadvantage is that the eye movements dissociate the position of the object in the world and its retinal position. So if I fixate in a certain place, a neuron in visual cortex, because of the retinotopic organization of most of visual cortex, will have something in its receptive field. And when I move my eyes, something completely different will be in the receptive field of the neuron. So whatever the neuron is analyzing, it has to start from scratch. And somehow these remapping of receptive fields has to be coordinated. It's an extremely complicated process. I'm going to show you next basically just what our visual system has to do while it's making saccade after saccade. And I'll use again this image of the castle. So when you look at this image, you might start by fixating at the center, and basically the rest of the image is functionally blurred. It doesn't look blurred, but the high acuity information is not accessible. So to pick up information across the visual field, you have to move your eyes around by jumping from place to place. And as you jump from place to place, basically at the position where you land, you need to do your visual system needs to do 3 tasks. First of all, you need to recognize the object that's in the fovea. Second, you need to transfer that information into some kind of memory, some kind of visual memory, so that it doesn't get destroyed when you make the next saccade. And third of all, you need to compute the next position where you want to move the eye to pick up more information. And the amazing thing really is that our visual system can do all of these tasks so quickly within each single fixation. This just shows the scan path of how that particular observer moved their eyes across the image, and those scan paths have been studied a lot, and some people claim that it works really well to predict which parts of the image an observer will fixate, but it works just above chance, but not really well. But usually we don't really look at static images. And static images, I think the one thing we learned from measuring eye movements when observers are looking at static images is that observers mostly look at the center of these images. So that's not particularly interesting. But when just to illustrate these 3 tasks now again, when the observer fixates here and then makes a large saccade over here and then 2 small saccades, you can see the speed of the eye movement across 1 second here, and you can see the speed during the saccade is very high and we're functionally blind during these saccades, but the fixations in between can be relatively short as 150 milliseconds. And basically this object recognition, transfer to visual memory, and selection of the next saccade target, those have been shown to be, that they can be done in less than 100 milliseconds. So there's work on object recognition by Simon Thorpe in his lab in Toulouse, and work on even on iconic memory by George Sperling, my thesis advisor. All of these can be done very quickly, and it has to be done by the visual system. Now, the other big question is how we select the next target for our eye movements. And here, there's very nice work that has shown that when we just passively look at these images, it's very difficult to predict where people will look. But whenever we do something, whenever we have a certain task, it's very clear where people would look. They look at the locations that are important for doing the task. And Mike Land in England has done some experiments with some of the first experiments where mobile eye trackers were used at all. And he was looking at his own eye movements while he was making tea. And then some scientists from the United States have measured the eye movements while observers were making peanut butter and jelly sandwiches. And it was clear that no matter what salient objects were around in the lab, the observer basically only looked at the objects that were immediately relevant for the task, namely the peanut butter jar or the jelly jar or the slice of toast that were pouring it on. So whenever we do something, our eye movements are kind of the slave of the skeletal motor system. They need to bring the information that our motor system needs to do the task. And I'm going to show you now that this holds even for the simplest tasks there are. You could imagine, like one such task is walking. Now, this is an example from a colleague of mine from nearby Marburg, Wolfgang Einhäuser, and he had also a mobile eye tracker that not only tracked where the people were looking, but also where they had a head-mounted view. And these are two observers. One of the observer to the left is walking up this cobbled road in the old town of Marburg, and the observer to the right is just walking next to the other one up this irregular flight of stairs. And when I start this movie here, you can see that basically this observer is looking ahead and probably just trying to figure out what pub to go to when he's reached the top. But the other observer who takes these irregular stairs basically constantly looks down at the stairs just not to miss a step. So even when you walk down the street, you need your eye movements and the visual information that they get you to do this task. We did some experiments on visual grasping, where observers had to grasp objects with a precision grip with the thumb and their index finger, and we measured their eye movements either while they were grasping the objects or while they were just looking at the objects. So the setup is shown here. We had this plexiglass frame in front of a display screen, and these shapes were mounted on the plexiglass frame. And in one set of trial, the observer was initially fixating here and then just made a saccade over to the object. And in another set of trials, the observer was fixating, then had to grasp the object, and at the same time they looked at the object. Just shows an example trace. Here, basically the trajectory of the thumb and the index finger relative to the object. And the green curve here indicates the gaze. And you can see that the gaze here goes first to the center and then to the top where the index finger is contacting the object. And that was basically, typically for our experiments, when the observers were just viewing the object, all the saccades basically went to the center of the object. And that's a well-known fact, this center of gravity, preferred view location. But when they were grasping the object, the locations tended to shift towards the contact position of the index finger. Could have been the thumb, but it seems that the index finger has more degrees of freedom when touching the object, so it needs to be controlled more precisely. And of course, this held also when we rotated the objects around. So even for the most simple motor tasks are eye movements need to pick up the information that the motor system needs to, or that the visual system needs to guide this motor task. Now, what I'm going to show you now is that this similar thing holds for perceptual tasks. When the observer is, for example, making lightness judgments or size judgments. And of course, one example for a perceptual task that could not be done without eye movements is reading. So if you look at this slide here, or if you look at the display of your cell phone, basically, whenever you read something, you can only recognize a handful of letters at a time at the point of fixation. And in order to read a text such as this, basically you have to jump from word to word and then pick up all the information. Sometimes when there's a difficult word, you might go back a little bit, or sometimes you might skip a very simple word like this for. But basically, without eye movements, the reading would not be possible in this manner. You might say this is trivial, but it's actually, the amazing thing is that the landing positions of the eyes when doing this reading task not only depend on sort of the shape of the words or the letters, but also on the frequency of the words, on the predictability. Our eye movements are really highly optimized for picking up the information contained in text. But as I said before, I would like to go into other even more basic visual tasks, such as lightness perception and size discrimination. And this slide, which is from Eli Brenner's lab, illustrates the two basic problems we face when making such perceptual judgments with real-world stimuli, rather than this flat stimuli that we often use in the lab. Now, what you see here is a yellow grapefruit and a green apple, and basically it's trivial that you see this as yellow and of a certain lightness, but if you look at the distribution of pixels here within this object, you can see that they actually vary quite a bit. There's sort of small changes in pigmentation, and there's of course a shading gradient. It goes from bright to dark down here. So if you want to arrive at a judgment about the lightness of this object or about its hue, you have to pick up samples from the object and then combine them by some statistic to arrive at a single estimate of the color and the lightness of that object. That's what I call the sampling problem. The calibration problem, which I'll go into the second part of my talk, basically means that if you fixate at a certain point of this object here at the apple, and you see the grapefruit here in peripheral view, the activation in your visual system will be quite different from the activation that you get from the same object when you view it foveally. Because, for example, color sensitivity decays very rapidly in the visual periphery, and it decays differently for different colors. So in a way, so that the object doesn't change its color when you make a saccade from here to there, you somehow need to calibrate the periphery of the visual field with the foveal representation. And that's the calibration problem. But I'll start with the sampling issue. And we did a very simple experiment to look at how people sample information for lightness judgment. We just took a bunch of objects that happened to sit around in the lab and put them on a table that was covered with a black felt. And the observer had to adjust this patch of light here on a monitor behind the object so that it would match the object that was presented here. They could adjust the lightness, the hue, and the saturation. I'm only going to go into lightness today because the other two aspects, saturation and hue, are not particularly interesting. And while the observers were doing the task, we measured the position of their gaze, and we of course measured the ground truth, the true color of the object with spectroradiometric measurements. And the first and most important result is that the observers were able to do the task. So they did not ask, well, should I match this local luminance value here, or the local luminance value here or there, they knew that was required from them was to judge the reflectance property of the object, the invariant property of the object, how much light is reflected from the object. And it's very easy to do, though, because this local luminance measurement, basically the output of the retina, is not really accessible to our conscious perception. So when observers made these matches, they moved their eyes around, and basically this shows the result of the matches. On the y-axis now here is the luminance, and this vertical line gives the range of luminance values within the object. And the horizontal line is the average luminance within the object, and the gray area is the standard deviation. And what you can see here is that the observers don't use the average luminance within the object. That's the mean. That's here. This looks much darker than what the object looks to the observer. What they use is something, their matches, these are the data points here, the matches are very close to the maximum luminance value within the object, and it's also close to the upper limit, which is what you would get if you orient sort of the piece of paper cut out from the cone perpendicular to the light source. Now, so they do not use the mean, but they use the maximum here. And intuitively, that's a good strategy, because basically all the darker regions are due to the shading. They're basically due to properties of the orientation of the surface and not of the reflectance of the surface. But we want to know now, of course, why they would use the maximum and not the mean, and also how they arrive at this judgment. And how they arrive at this judgment, to answer that question, we want to look at the eye movements at the points where they fixate. And what you can see here is I've divided up basically the local luminance values within the object into 9 different bins. And what you can see here is that those regions that are very light, that are close to the maximum and close to the value that was used for the match of the observers, they basically are almost always fixated. And the regions that are very dim and are very different from the match the observers made are hardly ever fixated. So there seems to be a very close relationship between the perceptual impression that the observers have, and which they use for their match, and where they fixate. But of course, that's just a correlation now, and we would like to experimentally show that the fixation positions are important. So we would need to force our observers to fixate certain regions. And it turns out that we can actually do that using a gaze contingent paradigm. So now, in order to force the observers to fixate this red spot here, we basically display the object only when the observers really fixate right here. And when the observers move their gaze away, indicated by the green point here, we erase the object on the screen. And we present this red spot here so that they know where to move their eyes to. And when they do, the object immediately and magically appears again. When they move away within the object disappears, appears again. When they fixate the screen, it disappears. And when they fixate the matching disk and make their adjustments, the object is also visible and thus available for peripheral viewing. But this way, we can let the observers make their match while people are fixating a certain point. And of course, we want to know whether it makes a difference, whether they fixate a point that's here more in the dark region or a point that's here more in the light region. And it does make a difference. So this shows that when observers fixate a point that's slightly in the dark, they adjust a certain luminance value here, and when the observers fixate a light region, they adjust the object to appear brighter than when it's in the dark. So the position where we fixate the object has a causal and direct effect on our perception. So this means that the way we perceive the lightness of objects is driven by how we look at them. Now, if you think about that sentence, you might wonder whether that's a good thing or whether that's a bad thing. Because if I have an object and I sort of move around it or I rotate it, then I don't want it to change its lightness. I don't want this to appear lighter or darker depending on its orientation. So, in order to investigate whether the strategy of using the maximum luminance value within the object and fixating those regions of the object is really a good strategy, we ran a simulation where we used 50 or so of these three-dimensional shapes that are available on the internet of all sorts of different objects. And we used a software package, a physics-based rendering package called Radiance, to illuminate these objects with a natural light field. And basically what the software does, it calculates the physical intensities of the light that enter the eye of the observer. And then, of course, we can easily rotate the object around. And for each object, basically we end up with 400 different views. And then we can look at each statistic, for example, the mean, and calculate the mean for each one of these different views, and then see and evaluate whether it's a good statistic. Now, what is a good statistic? Well, a good statistic is one that's reliable, one that always gives the same answer, no matter what the orientation of the object is. And reliability has been a very prominent feature in many approaches, especially in the Bayesian approach to visual perception. We want our perception to be reliable. And the statistics we looked at here were the mean and also all the percentiles of the luminance distribution. And what you can see here is that the most reliable statistics, the ones with the smallest standard deviation, are the minimum and the maximum. And if you think about it, if the minimum, that would basically mean that you call all the objects black. That way you're perfectly reliable. There's no variability at all. And of course, that's pretty useless. So if you have a measuring instrument, for example, a scale, and every time you step on it, it gives you the same answer, 80 kilograms, then it's reliable, very reliable, but useless. So we need something else to evaluate our statistic, and that something else is the validity. You want the statistic to be diagnostic of changes in reflectance. So we did the whole simulations again, but we used two different pairs of slightly different reflectances, and we checked how well our statistics could differentiate between two slightly different reflectance values. And in that case, you can see that the maximum here is clearly the best there is. So basically what this result shows is that observers are very well advised to use the maximum as the statistics for estimating the lightness of these objects, and basically that by fixating the regions of the object that have luminance values close to the maximum, they really support that estimate and that strategy. Now, so the saccadic selection really optimizes the lightness perception in the task we used, but also in several other tasks we used. There's, of course, as you know, there's many different so-called lightness illusions, like this Adelson's checker shadow illusion, or most impressive, this illusion by Bart Anderson, where the luminance distribution within what appears to be black moons here is identical to the luminance distribution of what appears to be white moons on the other side. And we done experiments on this and showed that also in this illusion, basically the selection of fixation positions is really optimal to get the correct interpretation of the world and the correct estimate of the lightness. Now, in the second and shorter part of my presentation, I'd like to get back to the calibration problem. So, if you look, for example, if you fixate somewhere on the apple, I already told you that the sensitivity of the chromatic channels in the visual pathways decreases very rapidly towards the visual periphery. And if I simulate this decay here in this image, you can see that basically part of the grapefruit now has a very, when viewed peripherally, now has a very similar color to what the part of the apple has when viewed in the fovea. But still, I mean, we don't want the grapefruit to appear green when we look at it in the periphery, and then when we make a saccade from here to there, suddenly change its color to its yellow tone again. And the same way, of course, for the apple here. So we want our perception to be stable across and uniform across the visual field. And what I showed you for color is even worse for size, because if you look at the cortical representation of these objects, this is sort of a simulation of how the representation of these objects would look in primary visual cortex, for example. When you fixate at the orange, then the orange takes up a vast extent of V1, whereas the size of the apple here is much reduced in the visual periphery. And of course, the reverse then holds when you fixate on the apple. Now, of course, this kind of learning of to associate perceived size with the extent of things in visual cortex is something that must happen very, very early in development, probably at the same time as we obtain size constancy between 6 and 9 months of life. But there's been evidence from other adaptive processes like saccadic adaptation that these processes often can go on throughout life. And we wanted to investigate whether basically this size calibration would still work in adult observers. And basically, if we basically constantly learn this calibration between fovea and periphery, it could also, as I told you, serve as a way to gain perceptual uniformity across the visual field so that objects don't change their size or their color when we bring them in from peripheral viewing to foveal viewing. And this is a suggestion that has been made by Kevin O'Regan and Albanoe a while ago, but there's been very little experimental evidence for that suggestion that basically we use, for example, eye movements to associate the peripheral representation of an object when we view somewhere else, and then we make a saccade, and we can associate this now foveal representation to the former peripheral association. And in the extreme case, basically, when we have something in the periphery, we will be able to predict the effect it would have on our visual system once we made the saccade, and we can basically, for our conscious perception, just use this predicted value. And that's a very strong claim, and as I told you, there hasn't been much empirical evidence for it until now, but we performed experiments just to test that with size. And basically, our observers were fixating at an object. It was kind of a blurry circle at the center, and they viewed another blurry circle in the visual periphery, and they first had to do a size judgment. They just had to say which one of these objects looks bigger. And, well, they would indicate, for example, well, the object I'm looking at looks bigger. And then they make a saccade to the peripheral object, and then they have to do a second task. There is a tiny little protrusion on the peripheral object that's really a threshold, and it cannot be seen when you view it peripherally. And they have to say whether this protrusion is pointing down, up, left, or right. But that task is just to keep their attention on the peripheral object. The important thing here is that while the observers make the saccade, we change the size of the peripheral object and increase or decrease its size by 10%. And because we're blind during the saccades, basically observers do not perceive that change in size. And we actually explicitly measured thresholds for perceiving these size changes, and this 10% size change was way below threshold. So the observer doesn't really notice that anything tricky is going on. And so we do this for a while, and the question is, of course, when we consistently increase the size of the peripheral object, will it look bigger when the observer is still looking at the foveal object? And the results are shown here in this slide. These are the experimental trials, and here's basically the perceived relative size of the peripheral stimulus. And we had 3 groups of observers. For one group of observers, nothing ever changed throughout the experiments. That's the black line. For the other 2 groups, the first 100 trials just started out as for the control group. Nothing happened, and we just measured a baseline. And what you can see here is that the baseline is already kind of below the point where the objects are physically identical. That is, without any experimental variation, the peripheral object looks slightly smaller. But that is a well-known effect that has been found many times for conditions similar to the ones we used here, so we were just replicating this. But now, during the next 100 trials, we slowly and gradually sneaked in this size change because we wanted to be sure that the observers wouldn't notice anything. And after trial 200, basically the size change is fully in effect. And we use sort of 100 trials around each data point to calculate a psychometric curve and calculate the apparent peripheral size. And what you can see here is that for the decrease group, if there is a transsaccadic decrease in size, that leads to a relative decrease in the perceived size of the peripheral stimulus. And if there's an increase during the saccade, that leads to an apparent increase in the size of the peripheral stimulus, even though observers haven't made a saccade yet. So things look bigger then. This was after 400 trials, and we had our observers come back on the next day, and then we reversed the size change. The group that used to be in the decrease group now got the size increase, and the other group got the decrease. And basically the effects also reversed. But a really interesting thing happens here, which basically means that the change, the transsaccadic size change, the observers learned on the first day was still present when they came back into the laboratory on the second day. And this could basically either mean that the size change is very specific to the experimental situation, or because observers do go home and they do make some saccades in that direction without the size being changed. But it could also be that maybe they just don't make that many saccades. So now we're giving our observers mobile eye tracking equipment, and we're measuring the distribution of saccades people make during the course of the day to differentiate between these 2 conditions. Now this basically shows that there is such a recalibration process, and that could be the basis for our perceptual uniformity. And of course, this opens up many, many further questions. So, for example, is this an effect that's specific to the location that was learned, namely for saccades to the right, or does it generalize across the whole visual field? Or do we really need saccades, or is any other kind of prediction functional too? And just to give you very quick answers, the effect did generalize at least to the location opposite of the trained location. So we had another group learning it, and then we did the testing in the trained location and in the other location, and basically we found this interaction from day 1 to day 2 for both groups. So it seems that it's not a very highly specific change, but in the extreme case, and we're testing now many different locations, it could be that something like the cortical magnification factor, this M factor, is really what's being learned here. And to see whether saccades are really necessary, we had a second task where instead of the observer making a saccade to this peripheral stimulus, the peripheral stimuli would sort of make this wiggly motion until it arrived in the fovea, and during this motion, the size would change accordingly. And with that manipulation, there was still an effect, but you can see here that the effect was much smaller. So the saccades are really the best way to learn this contiguity between foveal and peripheral stimulation. So it's just a summary that recalibration is not strictly local and it can occur without the saccades. But to get back to the basic questions, what I've hoped that I've convinced you of is that even for very basic perceptual judgments like brightness or size judgments, the movements of our eyes are very important factors. And for lightness judgments, the sampling of information with our eyes is very important, and the size and for the size perception and probably other factors too, eye movements really help us to learn the association between the foveal and the peripheral visual field, to calibrate the complete visual field, and such enable us perceptual uniformity of our visual world. So in a way, the eye movements are what keep our visual world together. Thank you very much.